Global optimization is a branch of applied mathematics and numerical analysis that deals with the global optimization of a function or a set of functions according to some criteria. Typically, a set of bound and more general constraints is also present, and the decision variables are optimized considering also the constraints. Global optimization is distinguished from regular optimization by its focus on finding the maximum or minimum over all input values, as opposed to finding local minima or maxima. General. A common model form is the minimization of one real-valued function in the parameter space, or its specified subset. Here denotes the set defined by the constraints. In many nonlinear optimization problems, the objective function has a large number of local minima and maxima. Finding an arbitrary local optimum is relatively straightforward by using classical local optimization methods. Finding the global minimum of a function is far more difficult. Symbolic methods are frequently not applicable, and the use of numerical solution strategies often leads to very hard challenges. Applications. Typical examples of global optimization applications include protein structure prediction, computational phylogenetics, traveling salesman problem and electrical circuit design, chemical engineering, safety verification, safety engineering, worst-case analysis, mathematical problems, object packing problems. The starting point of several molecular dynamics simulations consists of an initial optimization of the energy of the system to be simulated, spin glasses, calibration of radio propagation models and of many other models in the sciences and engineering, curve fitting like nonlinear least squares analysis and other generalizations used in fitting model parameters to experimental data in chemistry, physics, economics, finance, medicine, astronomy, engineering, deterministic methods. The most successful general strategies are inner and outer approximation. In both of these strategies, set over which a function is to be optimized is approximated by polyhedra. In inner approximation, the polyhedra are contained in the set, while in outer approximation, the polyhedra contain the set. Cutting plane methods. The cutting plane method is an umbrella term for optimization methods which iteratively refine a feasible set or objective function by means of linear inequalities, termed cuts. Such procedures are popularly used to find integer solutions to mixed integer linear programming problems, as well as to solve general, not necessarily differentiable convex optimization problems. The use of cutting planes to solve MILP was introduced by Ralph E. Gomery and Vaclav Schvartal. Branch and bound methods. Branch and bound is an algorithm design paradigm for discrete and combinatorial optimization problems. A branch and bound algorithm consists of a systematic enumeration of candidate solutions by means of state space search. The set of candidate solutions is thought of as forming a rooted tree with the full set at the root. The algorithm explores branches of this tree, which represent subsets of the solution set. Before enumerating the candidate solutions of a branch, the branch is checked against upper and lower estimated bounds on the optimal solution, and is discarded if it cannot produce a better solution than the best one found so far by the algorithm. Interval methods. Interval arithmetic, interval mathematics, interval analysis, or interval computation, is a method developed by mathematicians since the 1950s and 1960s as an approach to putting bounds on rounding errors and measurement errors in mathematical computation and thus developing numerical methods that yield reliable results. Interval arithmetic helps find reliable and guaranteed solutions to equations and optimization problems. Methods based on real algebraic geometry. Real algebra is the part of algebra which is relevant to real algebraic geometry. It is mostly concerned with the study of ordered fields and ordered rings and their applications to the study of positive polynomials and sums of squares of polynomials. It can be used in convex optimization stochastic methods. Several Monte Carlo-based algorithms exist. Simulated annealing. Simulated annealing is a generic probabilistic meta-heuristic for the global optimization problem of locating a good approximation to the global optimum of a given function in a large search space. It is often used when the search space is discrete. For certain problems, simulated annealing may be more efficient than exhaustive enumeration, provided that the goal is merely to find an acceptably good solution in a fixed amount of time, rather than the best possible solution. Direct Monte Carlo sampling. In this method, random simulations are used to find an approximate solution. Example: the traveling salesman problem is what is called a conventional optimization problem. That is, all the facts needed to determine the optimal path to follow are known with certainty, and the goal is to run through the possible travel choices to come up with the one with the lowest total distance. However, let's assume that instead of wanting to minimize the total distance traveled to visit each desired destination, we wanted to minimize the total time needed to reach each destination. This goes beyond conventional optimization since travel time is inherently uncertain. As a result, to determine our optimal path, we would want to use simulation optimization to first understand the range of potential times it could take to go from one point to another, and then optimize our travel decisions to identify the best path to follow, taking that uncertainty into account. Stochastic tunneling. Stochastic tunneling is an approach to global optimization based on the Monte Carlo method, sampling of the function to be objective minimized, in which the function is non-linearly transformed to allow for easier tunneling among regions containing function minima. Easier tunneling allows for faster exploration of sample space and faster convergence to a good solution. Parallel tempering. Parallel tempering, also known as replica exchange (MCMC) sampling, is a simulation method aimed at improving the dynamic properties of Monte Carlo method simulations of physical systems, and of Markov chain Monte Carlo sampling methods more generally. The replica exchange method was originally devised by Sven Zen, then extended by Gaia, and later developed, among others, by Giorgio Parisi. Sugita and Okamoto formulated a molecular dynamics version of parallel tempering. This is usually known as replica exchange molecular dynamics, or REMD. Essentially, one runs n copies of the system, randomly initialized, at different temperatures. Then, based on the metropolis criterion, one exchanges configurations at different temperatures. The idea of this method is to make configurations at high temperatures available to the simulations at low temperatures and vice versa. This results in a very robust ensemble which is able to sample both low and high energy configurations. In this way, thermodynamical properties such as the specific heat, which is in general not well computed in the canonical ensemble, can be computed with great precision. Heuristics and meta-heuristics. Name page. Meta-heuristic. Other approaches include heuristic strategies to search the search space in a more or less intelligent way, including evolutionary algorithms, differential evolution, a method that optimizes a problem by iteratively trying to improve a candidate solution with regard to a given measure of quality, swarm-based optimization algorithms, mimetic algorithms, combining global and local search strategies, reactive search optimization, graduated optimization, a technique that attempts to solve a difficult optimization problem by initially solving a greatly simplified problem, and progressively transforming that problem until it is equivalent to the difficult optimization problem. Response surface methodology-based approaches. IOSO indirect optimization, based on self-organization. Bayesian optimization, a sequential design strategy for global optimization of black box functions using Bayesian statistics. Software. 1. Free and open source. OpenOpt. 2. Commercial. Lion Solver. TOMLAB for MATLAB. MIDACO global optimization software. Optimus platform. The NAC numerical library contains routines for both global and local optimization. Demo global optimization software versions are available also for a number of commercial software products. Extreme, a single and multiple objective optimization software for nonlinear optimization.